Hey everyone, Morgan here. So today we're going to be looking at something a little more complicated, and that is how electrons go into orbitals. And it is described by something that is called the AUFBAU Principle. Now, AUFBAU in modern German language would mean construction, and it's based on two words, auf, which is up, and bau, which is building. So really this is the building up principle. And what that tells us is that electrons build up from the lowest energy orbitals to the highest energy orbitals. Okay? Now when they do this, they follow something called Hund's rule. And I'm going to write a definition about this, but we won't understand it till we get to the next page. Electrons will singly occupy orbitals before they doubly occupy orbitals. And then the other rule that we're going to be using is called the Pauli exclusion principle. No two electrons can have the same set of 4 quantum numbers. Now, I know I might as well be speaking German here, okay? This is going to be going right over folks' heads. Don't worry about that. It'll actually make a lot of sense as we work our way forward in these next 2 pages. So this is called an AUFBAU chart. This is a graph with energy that goes up, telling us that the lowest energy orbital is the 1s orbital. The next higher energy is the 2s. And then there are 3 orbitals called 2p that are all at the same energy level. So electrons will go here, before they go here, before they go here, before they go to here, 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 there, here. Start to get the idea. We're going up. Don't worry, this chart's going to be hanging on the wall the whole time we're doing this stuff. And actually, the modern periodic table is based on this chart. So as long as you have a periodic table handy, you'll be able to follow along what's being explained here. Okay, so let's go to page 14 and let's start to use this table. And I've kind of recreated it right here. Hydrogen has 1 valence electron. So we're going to draw an arrow pointed up. Our arrow is just our silly way of representing an electron. Okay, there you go. That is what is called the electron orbital diagram. For hydrogen. Now, what if we have 2 electrons, meaning helium? One will go spin up and then one will go spin down. And that is what we called the Pauli exclusion principle on the last page. We can't put both electrons in the same orbital spin up. Now, does this mean electrons spin? No, it's based upon actually the magnetic momentum of the electron. It's an angular momentum thing. Okay, for lithium, spin up, spin down, spin up. And that's a good example of AUFBAU. We start at the lower energy orbital first, then we go to the higher energy orbitals. Then for beryllium with 4 electrons, spin up, spin down, spin up, spin down. Again, that is the Pauli exclusion principle. Now boron has 5 electrons. Spin up, spin down, spin up, spin down, spin up. Carbon's got 6, spin up, spin down, spin up, spin down. Now watch. Spin up, spin up. And that was what on the previous page we called Hund's rule. electrons singly occupy orbitals before they doubly occupy them, as long as they're all at the same energy level. The technical term for that is degenerate, believe it or not. Okay. Nitrogen, with its 7 valence electrons, it looks like that. Hund's rule on display right there. Then for oxygen at 8 electrons, spin up, spin up, spin up, and spin down. Fluorine, spin up, spin down, spin up, spin down, 3 ups, 2 downs. Neon, spin up, spin down, spin up, spin down, 3 up, and 3 down. Okay. Now, interesting to note something. Helium, the 1s orbital is completely full. Neon, the 1s, the 2s, and the 2p, completely full. Those are noble gases. Noble gases always have completely full outermost shells. For helium, the outermost shell is the 1s. For neon, the outermost shell is the 2s and the 2p. All right, sodium. Spin up, spin down, spin up, spin down, 3 up, 3 down, 1 up. Magnesium, gonna look like this. Aluminum, looking like this. Silicon, and it's going to be spin up for the last 2. Phosphorus, spin up, spin down, spin up, spin down, 3 up, 3 down, up, and up. There's a pattern here. I think the pattern is something that you can identify with. You can see it makes sense. Up, down, 3 up, 3 down, 3 up, 1 down. Chlorine, now it's worth pointing something out here. If you look at fluorine and chlorine, which are both in the same family, they have similar outermost electron configurations. We're going to end up calling that valence. Argon, everything should be full because it's a noble gas. There we go. Potassium. And you know, you're thinking you've got this, which you probably do already, but there's going to be some exceptions coming our way. And don't worry, we won't make a huge deal about the exceptions. All the way here through calcium, they've been very similar. Now, when we go to scandium, we have to go up to the 3D. I want to point something out here. 1s. Then we have 2s, then we have 2p. Then we have 3s, 3p. Then we have 4s. But next is actually the 3D. Every time you go up an energy level, you add a little subshell of orbitals. And we added the 3D when we got here. It just turns out that the 4s is lower energy than the 3D. Weird order, don't worry, the chart will be hanging on the wall. So scandium, it looks like this. Notice that I still do the 3 up first before I do the 3 down. It's a good habit to get into. And then there's 1 in the 3D. Titanium follows the same pattern. Everything that you would think it should do. Vanadium, also nice, very predictable. Just adding 1 electron each time. Now chromium is weird. There's a little exception that happens here. And anybody that tries to tell you we know exactly why this happens, they're lying to you. They're pulling your chain. We know it happens. We don't have a very good explanation. But what happens is there's only one 4s, and then the 3d is half full, 1 electron in each orbital. Now, it would make sense that this has something to do with stability, okay? Spreading it out, making everything half full, but we don't really have a perfect answer for that. There's a few exceptions like that. Don't worry about them. That's not something you're going to be tested about. And back to normal when we get to manganese. Okay. So like I said, these are called electron orbital diagrams. There's also something called an electron configuration. A lot of people use these terms interchangeably. The world's not going to end if you do that. Okay, but for an electron configuration, let's say helium. It's 1s squared. Let's say neon. 1s squared, 2s squared, 2p6. Okay, it's kind of a shorthand notation. It's nice, it works, it's easier. Most people do it this way. This tells you a lot more information. That's why this is a better way to do it, because it tells you how many unpaired and how many paired electrons you have. And unpaired electrons behave differently than paired electrons do. Okay, we're going to practice this a lot, as you can imagine. Thanks for tuning in. This is Morgan signing off.